Alright guys, in this video we're going to cover function composition, and this goes with section 6.1. And guys, I already have it kind of written out here, but this is just a function that's composed or made up of another function. And I wanted to do a quick example, for example, like an oil leak. Let's say we've got an oil rig that is leaking, and it's leaking in a manner which the oil is dispersing in a circular pattern. And if it's leaking in a circular pattern, then what we can do is we can estimate the amount of oil leaked using the area function. And the area is a function that's dependent upon R. So we're going to say the area of the oil leak when the radius is R is pi r squared. Now, let's say we know that the radius is increasing 3 feet per minute. So let's say we know that the oil is leaking at a rate in such that the radius of the circle is increasing 3 feet per minute. So what we can actually do is we can now write the radius as its own function with respect to time. So the radius with respect to time would be 3t, where t is the number of minutes. And then the nice thing about this is now, since we have this area function, which is in respect to radius, and we have the radius function, which is within respect to time, we can substitute this quantity into the area function. And so we'd have the area with respect to time would be pi times 3t squared. And so we get that the area with respect to time is 9t squared pi, once we square the 3 and the t. Alright, and this gives us the area of the oil leak with respect to time, and this is called a composite function because it's a function that is made up of composing two other functions together. Okay, and then so let's say we want to know how much oil, what's the area of the oil what is the area of the oil leak after, say, 10 minutes. So in order to know that, we'd have to know the radius. So we could technically do this in two steps. We could plug the 10 minutes into here and do 3 times 10 is 30, so then that would be a radius of 30 feet, and then plug 30 into the area function. That's one way we could do that. Or since we have the area with respect to time function, we can just plug that in and we'd get 900 pi, which is going to be what, 900 times 3.14, so roughly 280 square feet. No, 2,800 square feet, roughly. Alright, so what we're really talking about is, in a more algebraic sense and a less application based right now, is function composition is written as f of g of x. So f of g of x. And this can be rewritten as, with an extra set of parentheses, as f of g of x. Sorry guys. Alright, so the whole idea of this is we're going to start off with some input value, x, and g is going to grab it and send it to an output value, which we're going to call g of x. And then the f function is going to come in here and grab that output value and send it to another output value called f of g of x. So this is called, the g of x is considered the inner function, and the f of x in this case is considered the outer function, and we always work these from inside out. So as an example of this, let's say we have f of x equals x squared plus 2x, and we have g of x equals 4x minus 1, and it asks us to find f of g of 1. Well, this can be rewritten as f of g of 1 with an extra set of parentheses, and then we can see here the first thing we gotta do is we gotta figure out what g of 1 is. And g of 1 just means plug 1 into g, so 4 times 1 minus 1, which is 3. And so now this can be replaced, g of 1 can be replaced with 3, and this now reads as f of 3. And then f of 3 means plug 3 into the f function. So that's going to be 3 squared plus 2 times 3, which makes 9, plus 6, which is 15. So we say that f of g of 1 equals 15. So we started with 1, and g took 1 and sent it to 3, and then the f function grabbed 3 and sent it to 15. Okay, so we're just doing two successive functions, one right after another. Alright, and so we're going to go with the same two functions, f of x equals x squared plus 2x, and g of x equals 4x minus 1. And what I want to show you is that function composition is not commutative, which means if we switch up the order, we will not always get the same answer. So for example here, g of f of x. Notice it's not asking us to plug anything into f of x. So this is really just g of x squared plus 2x. We can replace f of x with x squared plus 2x. And then this just means go to the g function, 4x minus 1, and plug x squared plus 2x into that. And so then from here we get 4x squared plus 8x minus 1, and nothing combines, and therefore that'd be our answer to g of f of x. Now let's say we take the two functions and we switch them, f of g of x. This means plug g into f. So this would be written as f of 4x minus 1. And then that means go to f, x squared plus 2x, x squared plus 2x. And where the x's are, put 4x minus 1. And then 4x minus 1 is being squared, so we're going to do 4x times 4x, 16x squared. 4x times negative 1, negative 4x, doubled, negative 8x. Negative 1 times negative 1 is positive 1. We're going to distribute over here, and we get 8x minus 1. The 1's cancel, the 8x's cancel, and so we get f of g of x just ends up equaling 16x squared. So we see here that g of f of x does not equal f of g of x. They do not give us the same value. Okay, so for that reason, function composition is not considered a commutative operation, because switching the order does not necessarily result in the same answer. Okay, so that's a big thing to follow. And the last thing I want to cover with this example here specifically is what's called an iteration, g of x. So this would also be written like this in this alternate notation, which is g of 4x minus 1. And what this means is you're going to go to the function 4x minus 1, and you're going to plug 4x minus 1 into it. We see this a lot with like computer programming, where we need a program to run a specific code over and over and over again to get a more and more accurate answer. Just give me a second and I'll show you an example of that. So finishing this up gives us 16x minus 5. Programming. This is a there we go. This is a function that's given for calculating the square root of a number. So for example, like we can type square root of 7 in our calculator, and the calculator gives us a very accurate decimal out to several decimal places, but someone had to program the calculator with the specific operation on how to get that decimal. It's not like the calculator just has all the square roots stored in it as a big list. So when you type in square root of 7, the calculator has to go through some kind of algorithm to get to what the decimal approximate answer is. And so I'm not for sure what the exact algorithm is in the calculators, but here's an example of an algorithm that will work. If we let x equal a plus 1 over all divided by 2, and we let the function be a divided by x plus x all divided by 2, then the square root of a number is approximately the composition of this function 4 times. So what that means is we're going to, so for example, let's say we want to find out what the square root of 7 is. Well, then x is going to be, using this formula up here, is going to be 7 plus 1 divided by 2, which is going to be 4. So then the square root of 7 is going to be approximately f of 4. So let's figure out what f of 4 is. We're going to plug 4 into this function. A, which is 7, divided by 4, plus 4, all divided by 2. Now guys, I know we could do this manually, but I'm going to, off on the side, I'm going to do this in the calculator. 7 divided by 4, plus 4, all divided by 2. Gives us that this is equal to, not approximately, this is equal to 2.875. So now we need to figure out f of 2.875. Well, f of 2.875 is going to be 7 divided by 2.875 plus 2.875 all divided by 2. And so I'm going to type that in my calculator. 7 divided by 2.875 plus 2.875 all divided by 2. And now I'm going to say I get approximately 2.65489. So then now I need f of 2.65489. And if I plug this into the function, I get f of 2.65489 is approximately 2.645767. 2.645767. And then if I plug that into the function, which will be the last time we'll do this, I get 2.6457513111. So I ran through this function 4 times, for that's called 4 iterations, and I get the answer. So square root of 7 is going to be approximately equal to f of 4, which is going to be approximately 2.6457513111. And if you go into your calculator and type in square root of 7, and then you'll see that you do indeed fact, the calculator does indeed fact give us that answer. Okay, so This allows a calculator or any kind of computer. This is the line of coding that says if you have a calculator that's programmed to do division and addition. So I can use addition and division along with this concept of function composition to figure out any square roots. Okay, so when you type a square root in a calculator, it's running through some kind of algorithm, not necessarily this one, but some kind of algorithm similar to this to give you that decimal approximate. So that's just an example of one specific application of function composition I wanted to hit on. Getting back more into what you're going to be expected to do in the homework. So I talked about how we have f of g of x. G of x is considered the inner function, and f of x is called the outer function. And this is a function composition, and we're going to call it h of x. Okay, so we're going to just say we have a function h, which is made up of f of g of x, where g of x has been plugged into f of x. So if we were said, given that h of x equals f of g of x, a popular thing that we see in calculus is determine f of x and g of x if h of x is equal to 2x minus 1 to the third power. Okay, so one of the things we see in calculus, which is kind of like u substitution also that we've done earlier in this year, is sometimes we need to figure out what is the inner and the outer functions in order to be able to work with them. So if we look here, we should be able to see that there's the inner function is 2x minus 1. And what would I plug 2x minus 1 into to get 2x minus 1 to the third power? Well, I'd plug it into x to the third. So we would say g of x equals 2x minus 1. That's the inner function. And f of x is equal to x to the third. That's the outer function. And if I take 2x minus 1 and I plug it in to x to the third, I get 2x minus 1 to the third, which is indeed h of x. Okay, so some of the homework questions are going to just be simply say, here's a composite function. Figure out what the inside function and what the outside function is. So and guys, don't overthink it. Let's say we've got the function is the square root of x plus 1. Well, the inner function is going to be the x plus 1, and the outer function is going to be the square root. So we say square root of x. Okay, so that's pretty straightforward. Don't want you to overthink that, but I want to take a second and hit that. Now, one other thing that we're going to need for the next section, which deals with function inverses, which is going to be showing that two functions are indeed inverses, is we need to be able to show that f of g of x equals g of f of x. And I know you might be thinking, wait a minute, a few minutes back you said in the video that f of g of x and g of f of x don't equal because the commutative property doesn't hold true. And that is true. The commutative property does not always hold true, but sometimes it holds true for specific functions, and that's what's called function inverses. If the two functions happen to be inverses of each other, then f of g of x and g of f of x do indeed actually equal, and actually more specifically they both equal x. So for example here, show that f of g of x equals g of f of x. Well, f of g of x just means plug g into f. So I'm going to write out f, 3x minus 4, and I'm going to plug g into it, x plus 4 all over 3. Now, since this is all over 3, and we're multiplying by 3, the 3's cancel, which gives us x plus 4, and then we bring over the minus 4, and then the plus 4 and the minus 4 cancel, and we get just x. Okay, so we know that f of g of x simplifies down to x. Now let's figure out what does g of f of x simplify down to. So this means plug f of x into g. So we're going to start with the g function, x plus 4 all divided by 3. And we're going to plug 3x minus 4 into it. Now, since there's an addition on top, the parentheses are not necessary. And in this case, the 4's cancel first, which leaves us with 3x divided by 3. And 3x divided by 3, the 3's cancel, leaving us with just x. So we see that g of f of x turns into x. So the transitive property says, since they both equal x, that means that f of g of x has to equal g of f of x. Okay, so there's going to be some questions in this section that just ask you to do that. And then the last thing that's going to be covered in this section is finding the domain of a composite function. Okay, and the kicker here, the big thing to realize is the domain of a composite function is the combined domain of the inner function and the composite function. Okay, so quick example, and then we'll do one that's a little bit more detailed. F of x equals x squared plus 2x. G of x equals 4x minus 1. If we wanted to figure out what is f of g of x's domain, well, the inner function is g of x. And since g of x does not have any divisions and it does not have any square roots, the domain of the inner function is negative infinity to infinity. And we've already worked out f of g of x. We already did that earlier in the notes. This is the one that ended up being 16x squared. And so the domain of the composite function, so this is the composite function, there's no division, there's no square roots. So the domain of this is negative infinity to infinity. And it's the combined domain. Well, since they both have a domain of negative infinity to infinity, the domain of f of g of x is negative infinity to infinity. Okay, now that doesn't always hold true. Let's say we've got this example. Let's say we've got f of x equals 1 over x plus 2. G of x equals 4 over x minus 1. Alright, so if we want to find the domain of, let's say, g of f of x, so we have to first figure out the domain of the inner function, which is going to be f of x, which is 1 over x plus 2. And see, this has the excluded value of x cannot equal negative 2 because that would cause a division by 0. So the inner function's domain is negative infinity to negative 2, negative 2 to infinity. Then we've got to figure out, well, what is g of f of x? And g of f of x means plug f of x into the function g of x. So 4 over 1 over x plus 2 minus 1. And then we're going to start simplifying this. So this is going to be 4 over, we're going to times this 1 by x plus 2 on top and on bottom. So we get 4 over 1 over x plus 2 minus x plus 2 over x plus 2. And then that gives us 4 over 1 minus x plus 2 gives us negative x minus 1 over x plus 2, because we can now subtract the numerators and bring the denominator along. And then now we're dividing by a fraction, so we're going to actually times by the reciprocal, which gives us the final function composition is 4x plus 8 over negative x minus 1. And negative x minus 1 cannot equal 0. And if we solve this out, we get x cannot equal negative 1. So once we work this out, we have the domain of this is negative infinity to negative 1 union negative 1 to infinity. But since this function is composed of this inner function, this part has to be included in the domain. So we wouldn't say the domain is negative infinity to negative 2, negative 2 infinity. We wouldn't say the domain is negative infinity to negative 1 to infinity. It has to include both of these. So the domain is going to be every number besides negative 1 and negative 2. So therefore the domain of this composite function is negative infinity to negative 2 union negative 2 to negative 1 union negative 1 to infinity. So guys, the kicker here is you find the domain of the inner function, you work out the composite function and find its domain, and then the domain of the composite function is the addition of those two domains. So you take the excluded values and you combine them to write out the entire domain. Alright, I hope that makes sense, guys. If not, email me questions, but this gives you everything you need to cover all of section 6.1's assignment. Thanks.